All right. And so for our final talk of this session before our break, we have Debbie Bard from NERSC, who's going to join us via Zoom. So Debbie is the group lead for the Data Science Engagement Group at NERSC, which is the National Energy Research Scientific Computing Center at Berkeley National Lab. She obtained her PhD at Edinburgh University and then worked at Imperial College London and then here at SLAC, where she was an LSST postdoc and then project scientist. And at NERSC, Debbie focuses on data-intensive computing and research. And we are very fortunate to have her virtually in the room with us today to tell us about experimental science and supercomputing, data-driven discovery using HPC. Take it away, Debbie.
Great, thank you. Hopefully you all can hear me okay. I'm very sad that I can't be there with you in person today, but I probably have COVID, so here I am joining you remotely. So what I wanted to talk about was a little bit different from what you'll hear in the other talks in this session. This session, we're focusing on data-driven discovery, but what really interests me about this topic is that it doesn't matter how great your data is, it doesn't matter how clever your algorithms are. If you don't have the right platforms to store and access that data, if you don't have the right platforms to run your software, then you're not going to make any discoveries from your data. And so that's what I started to get interested in when I was working at KIPAC, and it's what brought me to NERSC. And at NERSC, we're really at the intersection of scientific discovery and cutting edge computing hardware and technology. And that's something where I find very exciting. There's a lot of opportunities there for a whole range of science. And I'm going to talk today a little bit about some of the work we've been doing at NERSC and more broadly within the DOE to support data-driven discovery on the DOE research computing platforms. So if anyone's unfamiliar with NERSC, excuse me, we are the National Energy Research Scientific Computing Center. So we're one of the DOE user facilities. We sit in the Advanced Scientific Computing Research Office, that's OSCAR. You might hear me refer to that later on. And we are the mission high performance computing and data facility for the entire DOE Office of Science. So what this means basically is that any DOE-funded scientist who requires supercomputing scale resources can apply to have time on our systems. So, some supercomputing centers are very selective about who they have run on their hardware. We are not. We are very broad. We have a very diverse user base. We have something like 1,000 different projects using NERSC, something like 9,000 users. And it's very much focused on enabling science. So the statistic we're probably most proud of is that we contribute to over 2,000 scientific journal articles a year. So we, of course, we're a supercomputing center. We deploy supercomputers. The main system we have on the floor right now is Perlmutter. You may be familiar with that name. We name our scientists, we name our supercomputers after scientists who have leveraged computing in their research. So Perlmutter is a GPU accelerated supercomputer. And we have something like approaching half an exabyte of data capacity, both within our tape archive and in our disk systems. And also importantly, and this will you'll see in a minute why this is relevant, we have a very broad connection to the outside world. We have something like a terabit connection to the broader scientific community via ESNet, the Energy Sciences Network, which is the Internet for Science, which you may or may not be aware is probably how most of your data moves around. So NERSC has a very well-established history. We have been around for about 50 years. In fact, next year is our 50th anniversary. And over the years, we've supported a huge number of scientists and projects from the other DOE experimental and observational facilities. And something that we've really become aware of probably in the last 5 or 6 years since I've been at NERSC, this is something that's becoming increasingly important. We are realizing how much the news from this community is growing. As you're sort of hearing a lot in this session, a lot of different science teams are producing a lot of data. And that data is increasingly needing supercomputing scale resources for analysis. So this is a growing part of our user base. And they challenge us, this community, of which I consider myself a member, challenges a supercomputing center in ways that are new and in some cases quite startling for us. And so I want to talk a little bit about some of the work we've been doing at NERSC to really support this community. So roughly 30% of our users at this point come from experimental and observational facilities. They use about 20% of the compute time and occupy the vast majority of our storage capacity. So the balance of kind of compute and data access needs are different in experimental and observational data communities than in your kind of more traditional modeling and simulation communities. So, excuse me, we realized probably 7 or so years ago at Berkeley Lab that all the work that people were doing in kind of disparate areas of the lab and in the computing sciences area were not very well coordinated to support this community. So we started to bring all the work that people were doing in computing research at NERSC and ESNet in the various user facilities. We started to bring this together under a concept called super facility. And the idea for super facility is to connect experiments and computational facilities, and not just connect them physically via the appropriate networking. That in itself doesn't lead to scientific success. For scientists to be able to take advantage of the kind of hardware and the kind of computing resources available, supercomputing centers, you need a lot of other services, a lot of other infrastructure to go along with that, and expertise and community. These are science teams that are working in completely different kind of silos in terms of the science they're doing, but they need to be able to share their work and share their solutions to problems which, as you'll see, look remarkably similar when it comes to the kind of models they need for doing computing. So this is something that I've been heavily involved in since I started in NERSC. And about 5 years ago, I kicked off what we call the Super Facility Project. So this was a coordinated set of work to kickstart the work, building the base infrastructure and services that we knew, we understood were necessary to support the scientists that we were seeing coming to NERSC. So the idea here is that we be able to support, and these are all things that we couldn't really do before, but we wanted to be able to support real-time computing, dynamic and high-performance networking, including software-defined networking, making sure that scientists can use those networks to move the data around where it needs to go, to have interactive access to that data through HPC-scale Jupyter notebooks, being able to do this all securely and with authentication with federated identity, and then leveraging the technology that we see being developed in the cloud community, container-based edge services, kind of Kubernetes-style services, which are not necessarily appropriate on a traditional supercomputer. So we have a platform, Kubernetes platform called Spin at NERSC, which supports these services. And then, of course, everything here needs to be automated. And this is a very new concept for supercomputing centers, having API-driven automation of every operation that a user or a workflow might want to do at the supercomputer. So a key part of the strategy behind this was to engage with multiple science communities across different science areas, and that are all challenging us in very different ways. So I've got sort of the set of the 8 science areas that we were working with initially. Obviously, this includes some familiar experiments for you, working very closely with DESC, with DESI, with LZ, also with LCLS, just at the site where you are at SLAC, and then working with light sources like excuse me, like the ALS, like the Molecular Foundry at Berkeley Lab, the Joint Genome Institute, and also fusion experiments. So working with a D3D fusion facility in San Diego and also a fusion facility in South Korea. So the strategy behind making sure we engage with this broad range of different science teams was that we wanted to make sure that the solutions and the services we're developing were not one-off. Like, we recognize that this is a community whose needs are growing. We're going to have to support more and more of this at NERSC. And so we wanted to make sure that everything we were doing were kind of general solutions. And In the 18 months since we finished the project, we've really seen a lot of uptake in the services that we've deployed, which is fantastic. This is exactly what we needed. You know, we have more than 20 science teams now using our real-time queues to process urgent data. Jupyter has been a fantastic success story. We have over 1,500 unique Jupyter users a month, which is similar to the number of users who use SSH to access our systems, which is a completely it's a paradigm shift in the last 2 or 3 years that this has happened. And so now we have to think about how we incorporate Jupyter really as a first class, perhaps as the #1 access method for our systems. We have more than 85 projects using Spin, and we have a huge number of projects using the API. And the statistic here, which is really fun, is that we're getting roughly 1 request every 2 seconds through our API portal. So this is something that's really taken off. So I just give you a couple of science examples, very different science areas, but as you'll notice, a lot of the work that they're doing looks remarkably similar from the perspective of service providers at NERSC. So one of our sort of key science engagements is with the LINAC Coherent Light Source. This is the LCLS facility there at SLAC. They use NERSC for real-time collaborative data analysis. So when not every experiment they run at LCLS needs supercomputing scale resources, but when they do need it, then they have an automated workflow that takes data from LCLS, sends it to NERSC, does all the analysis, controls the HPC scale data analysis, and provides the results back to display to the scientists in the control room within minutes of the data being taken. And this is the time sensitivity is really important here. For a facility like LCLS, a scientist is only allocated a pretty short amount of time on it, similar to how you might only get a few nights at a telescope. It's really important that you can see what you're doing with that data during those precious hours of beam time. And so it's no use kind of waiting an hour or 2 for your data to finish processing when you've only got 12 hours of beam time. And you certainly don't want to have to take the data home with you and then realize that your sample was misaligned all along. So being able to provide this real-time data analysis using our supercomputing resources is making a big impact for the scientists here. And it's a model that we're seeing increasingly from multiple different science domains. And another example is the National Center for Electron Microscopy. So this is a user facility based at the Molecular Foundry at Berkeley Lab. They have a very high data rate detectors capturing something like 700 gigabytes of data in 15 seconds. And so they have a slightly different model. They stream data directly from their microscope to compute nodes on Perlmutter at Berkeley Lab, where the data is analyzed and then the results displayed back to the user on a Jupyter notebook. So they have an app that's running on our Spin platform that controls all of this, controls the data movement, the compute, monitors the compute success, and offers interactive data manipulation and some level of machine learning capabilities from this. And again, this gives the scientists results within minutes of their scan and keeps them happy, which keeps us happy. So the third, this is just an example of some data that a postdoc in my group was working on this just 2 weeks ago. And this is just an image of gold nanoparticles, a scan that was taken just a couple of weeks ago using NSEM. So both LCLS and NSEM are using this service in production now and kind of on a regular basis. All right, so the last example I want to give is fusion science. So we've been working very closely with a couple of different teams of fusion scientists who are trying to leverage supercomputing to have more efficient time at the tokamak. And again, this is a similar time sensitivity as in the previous examples, but for kind of different reasons. So this is very much looking forward to ITER, the International Fusion experiments based in the south of France that'll be coming online in the next 5 to 10 years. That'll be producing enormous amounts of data, and they really will need to leverage the world's supercomputing resources to analyze that data in real time to help the scientists in the control room at the tokamak to be able to have better, more longer lasting plasma reactions. So the workflow is very similar here. Data is read out, all the kind of information from the sensors about the magnetic confinement field, all that comes to NERSC. It's analyzed in somewhat real time, often with an AI-based analysis. Then the results are fed into a simulation, so a digital twin. So they run a very quick simulation of the experimental parameters, and this gives feedback to the operators for how they should best update the magnetic field parameters. And this has to be done within about 15 minutes because that's the time between plasma shots in one of these experiments. So I guess what I'm hoping you'll be able to take away from this is these are very different science areas, but their workflows look very similar. They have very similar needs, and the infrastructure that we've been able to put in place kind of scales out across these different science areas. And I've deliberately chosen examples that are not cosmology and not astronomy, because I kind of wanted to show the breadth of the work that we've been doing at NERSC, and show. And this is of course also applicable to many of the cosmology and astronomy experiments that you will work on there. All right, so if you want any more detail about this, it was a tremendous amount of work from a huge team of people. We put out a report last year. You're welcome to Google that and look it up for more details. But I want to talk a bit about some of the future implications for this, supporting this kind of model of science. So this is a chord chart showing how users from the different DOE user facilities use multiple facilities. So you don't need to know what all of these different acronyms mean. What the important thing is to note that the three here ringed in red are the OSCAR user facilities, so the computational user facilities in DOE. And there's a lot of overlap, particularly at NERSC, which is here on the left. Most of our users are also users of other facilities, and workflows span multiple computing centers. And this is something that we've been talking about within the Department of Energy Office of Science for a number of years now. And this has kind of come together in the concept called the integrated research infrastructure. So the idea of this is to kind of offer scientists who use DOE resources the opportunity to put those resources together so they can really leverage the full power of what the DOE has to offer. This is all in order to radically accelerate discovery and innovation. And if you squint at this image, it looks an awful lot like the super facility model, which is not a coincidence. You can think of the super facility model as kind of a lower dimensional representation of IRI, the integrated research infrastructure. We were working closely on kind of point-to-point engagements where an experimental facility is using NERSC. For IRI, we want to broaden this so that experimental facilities can use each other's facilities more easily, and scientists can use any of the advanced computing centers that DOE provides. So this is something that I've been involved in working on this and developing this over the past couple of years. And this is now a program at the Department of Energy. We've been working in a series of community activities, and I know some of you in the room were involved in, to design a reference architecture for this strategy and what this is actually going to look like. So this is kind of getting kicked off. This is all very exciting at the moment. Early projects and test beds are being defined. And there's also been a recent call for the establishment of an entirely new DOE user facility called the High Performance Data Facility, which I think you're going to be hearing a lot more about in the next couple of years. This is designed to be a distributed data facility that will be complementary to the supercomputing centers, and I think will be really useful for a whole range of science. All right, so we've had to think about this and take all these kinds of things into consideration at NERSC when we think about planning for our next system. So we are right now, we have Perlmutter on the floor, but we're starting to think about and design and architect our next supercomputer, which is the NERSC 10 system, because we're supposed to be deploying that in 2026, and that's coming up pretty fast. So we've really taken to heart the lessons we've learned from the super facility work and the requirements that we're hearing from science teams, particularly as part of the integrated research infrastructure. We've taken all that to heart in the design of this system. We understand that the HPC facility workload balance is evolving. We traditionally think of people doing simulations, perhaps people doing some AI work, people doing experimental data work. And in the past, they've been quite separated. But we're seeing the workload now evolve to more complex workflows where scientists might be doing simulation, AI training, and experiment data analysis all at the same time, similar to the fusion science use case. And we're seeing this happening more and more, and we're anticipating that that's going to be the dominant mode of use at a supercomputing center in the NERSC 10 era. So that's what we've been working towards for our system. So the mission need statement for NERSC 10, we're going to accelerate end-to-end workflows and enable new modes of scientific discovery through integrating simulation, experiments, data analysis, and AI. And this point of accelerating workflows is a really interesting one, kind of from the computing science perspective. And if you're interested in learning more about that, we have a white paper that kind of goes into our definitions of what a workflow is and what some of the challenges are in running workflows on supercomputers, and how we see hardware from the vendor community, the computing architecture community, kind of fitting into that. So I won't go into this into detail, but just to call out some of the themes that we are looking for in the end-to-end system. Looking for quality of service, we're looking for tight integration of all the components so that workflows can be easily designed. Things have to be portable, again, keeping in mind for IRI. We have to have APIs to do everything, and particularly security is something that is always important, but there's an increasing focus from the US government on the security of the national resources like supercomputing facilities. So this is something that we're increasingly paying attention to. All right, so that's all the contents I wanted to give you. We're really focused on accelerating end-to-end workflows for new modes of discovery. We really pioneered this concept through the super facility model, pioneering new modes of access to our systems, and really going beyond simply providing compute hours and storage capacity. We can now we've deployed a lot of different services and infrastructure to fully support urgent and complex workflows from experimental facilities really all around the world at this point. And all the work we've done there is informing our technology choices for N10. And looking ahead, we're going to be focusing on integrating across all the DOE user facilities. This is the vision of the integrated research infrastructure, because this is really how we see we're going to amplify the impact of science in the future. So this is certainly not an easy thing to achieve. There are lots of challenges, but it's one of the things I think is most exciting in developments in HPC, and that's why I wanted to talk to you about it. All right, thank you.
Thank you, Debbie. Questions, please raise your hand in the room or on Zoom. Start with Dan.
Hi, thank you for that super fascinating talk, Debbie. So I was interested when you were talking about the Perlmutter facility and the GPUs and the CPUs. I wonder if you had any insight on maybe how the balance is shifting between compute work on CPU platforms, on GPU platforms, and if there's any other emerging technologies that might start moving this around over the next few years.
Yeah, so I started getting interested in GPU work when I was at KIPAC, really when GPUs were first, and this is NVIDIA GPUs, right? When GPUs were first kind of being touted for general purpose computing. And so that was probably 10-ish years ago, and maybe 15 years ago. And over time, yes, a lot of scientific computing has been able to leverage the compute power from GPUs. But I think there's a bit of a mismatch between the expectations in the scientific community and expectations from the vendor community about how easy it is to design algorithms and to run your data analysis on GPUs. So all the increases in power and performance and really sort of technology focus is on GPUs. It's not so much on CPUs anymore. So there is a little bit of tension there, like between how easy it is to use a GPU and how the performance and kind of the capabilities that GPUs offer. You know, it's not easy to use them, but they're tremendously powerful if you can use them. Now, the other part of the question is I kind of want to answer in terms of usability. There are a lot of custom hardware sort of options out there. You know, we've looked at some as part of our vendor survey for the NERSC 10 system. Some of them are incredibly powerful. They are all very specialized, and they are all very hard to use for general purpose community. And at NERSC, we have such a broad set of users that we can't realistically deploy specialized AI machine learning hardware. That's actually very hard to use, specialized AI chips. And we can't necessarily justify deploying that to the broad scientific community, but they're incredibly powerful if you have the time and the patience to figure out how to leverage it. So at NERSC, we're really focusing rather than on kind of the most specialized hardware. We're looking at innovations in software and kind of new models for administering systems, new models for enabling both traditional HPC access and Kubernetes style cloud native use of supercomputing. We see that as being kind of a more beneficial area for the general science community.
Debbie, this afternoon, we're having our KIPAC in the World session. And while we have you here now, I'm curious if you could tell us just a little bit more about your path to this leadership role at NERSC. Maybe thinking back to your time at KIPAC or even grad school, is this a path you envisioned for yourself? And if not, what were the things that really prepared you to take on this challenge?
Oh, that's an interesting question. No, this is not somewhere that I envisioned myself being. I can tell you when I started grad school, I had taken one class in computing and I was working in particle physics, and they sat me down in front of a Linux box, and I didn't know what this was. I didn't know how to get started with it. So it's been throughout my whole career, very steep learning curve, kind of going from knowing absolutely nothing about computing to realizing that my entire career was based around data science. And it's really all been sort of, I find it really interesting to understand how to leverage hardware, leverage technology to get science done. There's a lot of unused potential in kind of computing technology that could really do not just sort of faster science, but allow us to answer new questions. And a lot of the work that you're seeing in AI, machine learning, none of that would have been possible without the GPU technologies that we have these days. So I find that exciting and really fascinating. And when I was at KIPAC, as I said, I by accident I got interested in GPU programming. I saw a talk at a conference once. And there was a couple of other people at KIPAC who were also interested in GPUs, and we kind of taught ourselves and started to understand what the possibilities were there. So moving into the role that I have at NERSC now, this is it was for me a logical move to kind of move to the other side, rather from the user perspective moving to the support perspective. And I'm just very enthusiastic about all the different types of science that we support at NERSC, which has kind of brought me into contact with a lot of very cool projects, which kind of brought me into the role I have now.
And I'm sure inspiring for the students in the room. You never know where your path from KIPAC will take you. Any last burning question before we move to our break? Oh, yes, one more.
Yeah, thanks for that talk. That was super interesting. It's really cool to see the tools like Kubernetes and other things that are being brought in from commercial cloud and all of the development there. So my question is, looking forward, how do you see that kind of collaboration with or learnings from the developments in the commercial cloud space being able to be brought back into the NERSC ecosystem to be able to improve the NERSC ecosystem?
Yeah, this is something that I think is essential. And there's two main reasons for this. One is that the younger generations of scientists have been trained largely on cloud computing. So they come with expectations of being able to run Kubernetes-based deployments and kind of applications that are really designed for cloud computing and not necessarily well supported on a supercomputer. So that's one of the driving reasons that we're adopting. We have to be able to adopt Kubernetes style deployment. And the other driving force here is that is the complete shift in the focus of computing manufacturers and the vendor landscape in the last 5 years. This is a huge change from when we were procuring our Perlmutter system. HPC centers and research supercomputing is no longer driving innovation in supercomputing. We are no longer the big ticket customer. You know, we spend hundreds of millions of dollars on a system. That is no longer a lot of money in this world. Everything is being driven by hyperscalers, by sometimes more specialized cloud computing providers, but still that's where the money is. And so we have to adopt that. Otherwise, we will be falling behind in terms of where the technology innovation is going. And so that's also something we have to look at in terms of the hardware, not just the platform like supporting Kubernetes, but also the hardware, like making sure we have the right networking, the right storage model to support the applications and kind of take advantage of the innovation that's happening in the vendors' sphere at the moment.
Wonderful. And that concludes our morning session. Let's thank Debbie again and all our speakers.